হ্যালো সুতনা, তুমি এখন হোস্ট। হ্যালো,
Yes, sir. Thank you.
হ্যাঁ।
Hello, am I audible? Hello.
Yes, ma'am.
Okay, so shall we start? Hello.
Yes, ma'am. I think it's 10 people are there.
Okay, so we can start, right? Uh, so what we'll do today is we'll solve the problems that were some of the problems that were assigned in the first assignment. And so, can you guys write in the chat which problems you've had, say, some difficulties with, so that we can solve them first and then move on to the others? Okay, five, and six. Any other problems? Okay, so we'll wait for like 3 more minutes. I suppose like some other people might join as well. So after 3 minutes, we'll start with problem five.
Okay.
Okay, so we'll start with problem 5. I'll read out problem 5 first, and so problem 5 says, suppose G is a simple connected graph and S is the set of all spanning trees of G. And we say that spanning trees T and T prime are neighbors of each other if and only if T contains exactly one edge which is not in T prime, and T prime contains exactly one edge which is not in T. So, and we constructed a simple graph G prime, which in such a manner that G prime has a vertex for each spanning tree in S, and any two vertices in G prime are adjacent if the corresponding spanning trees are neighbors of each other. Like, two vertices are adjacent means there is an edge between them. So first, like, I'll give you like a few, like, for what this is. Okay, so consider this graph. This is a bad drawing, but like, consider this graph, and this is the graph G. And S is the set of spanning trees of this graph G. So, and let G prime be the new graph that we have constructed. Note that even though V prime is a subset of V, E prime may not necessarily be contained in E. That is, E prime may contain edges which are not in E, where G is V comma E. So also another thing, if somebody has to say something, uh, and I cannot see chat while I'm looking at the screen, so like, if possible, please unmute yourself and feel free to interject. So what we'll first prove is that, like, if, say, T and T prime are two spanning trees, T and T prime may not necessarily be neighbors. They start with two spanning trees, and we'll prove one thing, that we can have a sequence of spanning trees starting from T to T1, say, sorry, T1, T2, up to some Tk, and then T prime, such that T and T1 are neighbors ti ti plus 1 are neighbors for I in 1 to k minus 1, and tk t prime are neighbors. So if we can show this, then we'll be able to show, since each of these are and also like note that like ti is not equal to ti plus 1 for all I in. So if we are able to prove this, we'll have one vertex from each of these. So we'll have, say, v from t, v1 from t1, vk from tk, and finally say v prime from t prime. Now, these vertices may not necessarily be distinct, but what will be, so this will prove that, so this will prove that sorry, is anybody saying something? um can you is if anyone's saying something, can you unmute yourself? Oh, why is v prime a subset of v? Okay, since you're choosing a vertex from the set of vertices, so obviously v prime will be a subset of v.
Ma'am, what are the elements of G dash?
uh, there is no unique, there is not necessarily a unique way to construct g dash. Like for instance, like the graph we have given here, like say, let's say we number these, let's number these. ठीक है? 1 2 3 4 5 6 7. So if you note mane, like note one thing, that 7 is part of the vertex 7 is part of every spanning tree. So the graph g prime can just be the vertex 7 without any edges.
Ma'am, actually, G prime is
Or
a
it can,
set which is having spanning trees as vertices, right?
sorry,
By the question, it is saying that G prime is a graph which is having spanning trees as vertices.
g prime
Let S
g
be
prime
the set of all spanning trees of G.
yeah,
Then G prime is a graph constructed on this vertices S with edge is defined as T and T dash when they are neighbors like that. It is defined, right? And the spanning trees must have the number of how many number of vertices in G. There must be the same number of elements in spanning tree also, right?
yeah, in each spanning tree you have the same number of elements, as you have the same number of vertices as you have in g, but uh, the number of vertices in g prime may not be the same as g. So corresponding to each spanning tree you're picking one element. Say you have two spanning trees, but you pick just one element, you pick the same element which is, say, like common to them, and that can be like that, like that can be your verdicts. Like I don't understand your question, can you repeat it? can you repeat the question once more?
Actually, in question, G dash is defined like G dash. The elements are the vertices are spanning trees, ma'am. Can you see that? In question, it is defined like G dash. The vertices are the spanning trees in G dash.
Yes, exactly. Like say corresponding to each spanning tree, you pick one vertex, right?
Okay, ma'am. Now I got it.
Like say if you have say your set uh, where is the board? Say how do you add a new page here? This thing is not working. Ah, there. So if your set is say S, and say you have your spanning trees, say S1, S2. So just for convenience, just use T. Say your spanning trees are say T1, T2, say Tm. This is your set of spanning trees. So corresponding to each spanning tree, you get say one vertex. Say you get V1 corresponding to T1, uh, V2 corresponding to T2, and say Vm corresponding to Tm, right?
Yes, ma'am.
Yeah. And we'll
But
have to show
do these vertices are from V only, V itself,
it.
G itself?
It you can pick them from G itself, or you cannot. It really doesn't matter. You can just when it pick create a separate set of vertices, which is like say disjoint from V.
Yeah.
It is irrelevant for the purpose. So say you have this set, like let's assume that these are just separate these this is a separate set of vertices. Okay.
So these are V dash, right?
Yeah, say this is V dash. Okay.
Yes, yes, ma'am. That is what I'm trying to say next.
Okay. So let's pick any two elements from S, say Ti and Tj. Okay. What we'll show is we have a sequence T, say I1, T, Ik, such that Ti, Ti1, like consider this sequence such that we have
Ma'am,
yeah.
earlier you have written that V dash is a subset of V. I guess you wanted to write that the number of vertices in G dash will be less equal to the number of vertices in G? Because how
Yeah.
will it be subset? I mean, there is no link between the vertices, right?
Yeah, but like you can just like pick one corresponding to each, but it's not necessary. You can just pick a separate set of vertex.
Yeah, exactly. I'm saying that the number will be less, but subset will be, I guess, wrong to say.
Yeah.
Yeah.
So we have like Ti and Ti1 neighbors, uh, Tik plus 1 neighbors for each k in the set. Sorry, I've used k here, right? I should use something else. This, let's call this r for each k in this, and Tir Tj are neighbors. So we are going to construct something like this. That way we'll be able to show that between any two vertex vi and vj, there is a path that connects it. Because if we can find these neighbors, then there is a path from this to this and this to this for each, like from here to here, and like from here to here and so on, and eventually from here to here. So we'll be able to prove that this is a connected graph. Is that clear so far? So so we know that these two are not equal, right? So consider the set of edges such that E is in the, say, edge set of I, Ti, and E is not in the, sorry, let's do it the other way. So T is in the edge set of Tj, and it is not in the edge set of Ti. Okay? So what will happen, like, if we add this edge E to the set of edges that are in Ti. So Ti is a tree, and if we add this set E, we'll be getting a cycle, right? There will be a cycle somewhere because Ti is a tree. It's a spanning tree, right? Right? Like anyone? Does this name? Do I need to prove this or is this okay?
No, no.
So so this is fine, right? Or because like if because of course you know that the number of edges say in Ti is has to be n minus 1 if you where n is the number of vertices in G. So so if you add one more edge, there must be a cycle somewhere. It won't be a spanning tree. So so we have so now after we've added this, now let say E prime be the set of edges such that E is in EI and E is not in Tj. So for instance, if we say, so we want to remove an edge. So we have a cycle. Let C denote the cycle, okay? The cycle contains, say, edges E1 up to ET, such that we have, say, V1 connected to V2 by E1, V2 connected to V3 by E2, and so on, where Vt is connected to Vt is connected to say V1 by Et here. So we have this cycle. Now one of these edges do not belong, at least one of these edges do not belong to Tj. Right? Because if all of these edges belong to Tj, then Tj will contain a cycle. And that cannot happen. So one of these edges do not belong to Tj. Is that clear? Hello?
Yes, ma'am.
Yes, ma'am.
So let's pick that edge and call it E prime. Okay. Now we remove that edge E prime from this cycle. It is still connected. The graph is still connected because you can travel from every point to every other point. If you remove one edge from a cycle, the graph is still connected. Is that clear? Say you have a cycle and you just remove one edge from them, this one. You can still travel from every vertex to every other vertex in the cycle. I'm assuming that's fine. Does anybody have a problem? Any confusion, please feel free to speak up. Okay, I'm assuming nobody has a problem. So what we do is we remove this edge E prime, which is not in Tj. So we still have a connected graph which has one edge missing from this set and one edge added in from this set. So T1 is a set which contains all but one edge from Ti and at least one edge from Tj, right? Right? Okay. So nobody's saying anything, so I'll assume it's fine. So we'll keep on constructing the next T2 in the same manner. We'll add one edge from this set E prime and we'll remove one edge from this set E the similar way as we did before. And as we continue, eventually we'll be able to get our sequence TR, which will be neighbors to TJ. Is that clear? Is that clear?
Ma'am, can you explain again the construction of T1?
Yeah. So basically look at this set. Look at this edge set E. It contains the edges of EJ which are not in EI. Okay. So EJ is the set of edges in TJ. And EI is defined in the same manner. So basically what we are doing is taking one edge from TJ which is not in TI, adding it to TI, removing one edge in TI which is not in TJ, and we keep repeating this step every time so that we include one edge in TJ which is, so we keep including edges of TJ and remove edges of TI. Eventually we'll end up with, so that we end up with TJ. Is that clearer?
Yes, ma'am.
Okay. So you see how we repeat this process. So
Ma'am, when it will stop, ma'am? When it will stop at TJ?
when we have exhausted E and we have completely incorporated E prime, note that the cardinalities of E and E prime are the same, because Ti and Tj, they both have n-1 edges, where n is the number of vertices. So the number of edges missing in one set will be the same number of edges missing in the other. So when we exhaust E, we'll have completely incorporated E prime if we go via this process.
Yes,
Okay.
ma'am. Get it.
And you get a spanning tree at every step.
Ma'am, we can think like that if we are removing an edge from a spanning tree, that will be disconnected, right?
Yep.
So
Yeah,
there
but
will be, yeah,
the first thing we're doing is we're adding an edge to the spanning tree so that it's no
yeah,
longer a spanning
yeah,
tree.
I'm saying that only that I was planning on like I'm deleting an edge from a spanning tree, then it will be a disconnected graph, so it will have two components. And if TJ is another spanning tree, as it is connected, it should have an edge between those two components, right?
Yeah, it's basically, we are basically doing the same thing.
Yeah,
So
yeah,
if
yeah.
it's another spanning tree that is distinct from this, then how will you choose the edge? So this is how we are going about it. So
Yeah, yeah, got it.
they can have a lot of common edges as well. You have to also have an approach towards how to pick the edge. Like
Yeah,
if you
that edge
are
should
going,
be uncommon, ma'am. Means like you take for E, take as E. The
I'm
edge should
sorry.
be, you are taking the choice of
Yeah,
edge,
like
right?
the edge should be the
In
edge should
T,
not
and it should
be,
not be in E, T dash,
yeah,
means
and also
TJ.
the edge that you're removing from Ti should not be in TJ
In
as well.
TJ.
Yeah.
Ma'am, and each iteration we will have a neighboring spanning tree, right? After each iteration step.
Yeah.
Oh, that's why it is going to be a connected after like
Yeah,
that.
yeah.
Okay, okay.
So everybody clear? Okay, so we'll be doing problem 6 next. So, so basically, so everybody clear about it, right? Hello?
Yes, ma'am, it is clear.
Okay. Okay, so problem 6. Let G be a bipartite graph on 2n vertices and degree of every vertex is 10. Prove that G has a perfect matching. Is everyone here familiar with the theorem called Hall's theorem?
Yes, ma'am.
Everyone, right? Okay. So can so I'm still stating it for like for completeness. If G's graph whose partitions are say A and B, and then there is a matching. The size of A if for every S which is a subset of A, so it's if and only if. Okay. So if and only for every S which is a subset of A, we have neighbors of we have the cardinality of neighbors of S at least as much as the cardinality of S. So this is Hall's theorem. So now let's construct a set P. Okay. Such that this is an ordered set so this is a set we create in our bipartite graph. Let's assume the partitions are A and B. So what is the cardinality of P? Does anybody have a guess? Can anybody think of a bound for P? We are also given that the degree of U is the degree of each vertex in G is 10. So can anybody think of a bound for P? So let's look at okay, like forget P. Let's take an arbitrary set S, which is a subset of A. Okay, and let's pick U sitting in S, right? So let n of U denote the number of elements with which are connected to U, which are adjacent to U. Okay, so let's consider all such sets. Okay, so clearly, say, let's call this say, let's call this P instead. So clearly the cardinality of P is greater than or equal to 10 times the cardinality of S. The degree of every vertex is 10, where so can you see why? Just look at how many times each element will occur. Like
10 times.
yeah. So corresponding to U, you'll have like this. So this is not even less than equal. This is basically equal to this. So U occurs here 10 times, right? In this set. And corresponding to each U, you get one of these. Okay? Is that clear? Is that clear, everyone? Hello?
Yes, ma'am.
Okay. So now consider each a random X in this, in a random NU. Okay, where U is in S. Okay, so how many times does how many times can X occur in here? At most 10, right? Because its degree is 10, and it cannot occur more than 10 times, right? Say
Yes,
if you
ma'am.
pick an element here, so if X is connected to, say, U1, U10, okay, now out of which all of these can be in S, or some of these can be in X, right? In S, right? Maybe a subset of this is in S. Maybe all of them are in S. But there are no more than 10 edges connecting X to elements of S, right? Is this clear? Anybody? So if we define the set NS, which is a subset of B, so that NS is the set of neighbors of S. So since this can occur at most 10 times in this set P, we say this is bounded by 10 times ns, because for each x in ns there can be at most 10 elements. So if we take 10 if we like multiply its cardinality by 10, which will definitely dominate the cardinality of P. Is that clear?
So
Is
10 into cardinality of S by using U, first coordinate,
Yeah, like
right?
just consider one element x from ns. Ns is the neighbor set of S. The neighbor set of S means there is an edge between one element in S and another element in NS. So
Here we are taking the number of elements of P. First one we took as in
yeah,
case of first coordinate. In case of first coordinate, and second we in case of second coordinate, that is X, right?
yeah.
In case
So
of first coordinate, it is 10 into cardinality of S. In case of second coordinate, means that is X. It will be bounded by 10 into cardinality of N of S, right?
yeah, like if we are basically trying to bound the cardinality of P, like we know what the cardinality of P here is, right? It's like 10 times mod of S. As you said, you will occur 10 times in P. Like P will have an element whose first entry is U for 10 of its elements, because there are 10 edges involving U, right? Just Consider the edge set. P is basically the edge set between uh, S and whatever points S is connected to. Okay, is it still not clear? Like,
Yes, ma'am, it's clear.
okay, so say this is the set A. This is the set B. And say this is your set S. Okay. So each of these have the same number of edges, and we're looking at the set P. Sorry, we're looking at the set P such that U is in S, X is in NS, where NS is the neighbor set of X S. So we're looking at all these edges, right? And we're trying to find a bound for the set P. So corresponding to each point here, corresponding to each point, we'll get 10 edges. So this is the same as this, right? As one of you said earlier. Is this clear, anyone?
Yes, ma'am. Since all the edges are from S to B, there must always be 10 times of quantity of S.
Yeah. So if we have this point is U. So U is connected to, say, x1 here and x2 here. So we are taking this edge and this edge. See, U x1, U x2. So if U is connected to two edges, we will get two entries here corresponding to U, like this, right? If U is connected to 10 edges, we'll get 10 entries here corresponding to U. So this part is clear, right? Now, let's look at the neighbor set. Okay. Now, X is connected to, say here, X is connected to U. X might be connected to some other point or might not be connected to some other point. So corresponding to, if you're looking at X, if you're looking at, say, if you have a point X here in NS and you want to see how many entries are there such that you have entries are there in P such that you have X as the second entry. So that's basically how many edges connect X. So say X1 is your X here. You see this is connected to U1. So corresponding to x1 you have this is connected to u. Corresponding to x1 you have u x1. There is nothing else here which connects u1 to anything. So you see there are like there are at most 10 elements which have 10 elements in P which have X in its second entry. So notice all the edges that are connected to X. It might, oh, এটা কি? Sorry. Oh, okay, whatever. So there might be an edge between x1 and something outside S. Not all of its 10 edges might be inside S, right? Right? So is this clear or not? Will anybody say something?
Yeah, ma'am, we can think in this way also, right? Means take all the edges of neighbors of S, means n of S. Okay, they will they are tending to cardinality of n of S, right? Take all the neighbors.
Yeah, this is basically that set. And
No,
there
I'm taking all the neighbors of n of S.
okay.
So then if we say that this all P will be in there in that set, means all the all the elements of S will be in that
Yeah.
set,
Yeah.
then that will prove that
Yeah.
cardinality of B is, means if the set is B, then cardinality of B is P should be greater than
Yeah.
equal to cardinality of P.
Yeah.
Then we can say cardinality of n of S is greater than equal to cardinality of S.
Yeah. That's basically the same thing, but the other way around. So you basically get this 10 times cardinality of n of S. And this gives you cardinality of S less than equals cardinality of n of S. So as we have shown as we have read in Hall's theorem, we have proven the condition for Hall's theorem, and therefore there is a matching. The size of there is a perfect matching. The size of A.
And
Okay.
Hall's theorem says there is a matching, right? No perfect
Yeah,
matching.
Hall's theorem says there is a matching the size of A. And here are the size of A, the set we are taking is the whole set A. This is N. And we have a matching from A to B. So this will have to be a perfect matching, right? N of each of these N elements connect to one element. So it exhausts all 2N elements.
Do we know that cardinality of A equal to N?
In bipartite graphs, it's usually referred when you say the cardinality of a bipartite graph is 2n. It's usually implied that it's split in A and B, each of whose cardinality is n. It is a convention.
That should be regular, right? If that is regular only, then that will happen, right?
I'm sorry.
If the graph is regular only, then that will happen, right? Cardinality of A equal to cardinality of B equal to N. If it is not regular, how that will be happen? Means cardinality of A will be N.
It is regular. It is like in the problem it's given that you have a bipartite graph on 2n vertices. Which it implies that you have like the partition is n, which the problem should have specified better, but it means that the partition is even. You have n in one and n in another.
And one more thing, ma'am, here in Hall's theorem, you're saying that there is a matching of size cardinality of A, or there is a matching which has all the elements of A.
Yeah.
Is it size of A or all the elements of A? Means saturates A, saturating
If you What is a matching? A matching is if you have a bipartite graph here, say say this is a bipartite graph, right? And okay, and if you have a matching, the size of A, which means which mean which means each of A's element has a pair here. We can have some say other elements, doesn't matter, but
A. Size of A, he said, ma'am, that means it might have elements from B also. It might miss elements from A.
yeah, but if the size of A is if the cardinality of A is n, okay, so is anybody like is anybody clear on why the cardinality of A should be n? Or do we let's okay, for instance, let's assume that there is you can do this on A. Okay, you have a perfect matching from A to B. Let's assume that there are elements in B, okay, that is not covered by A. Okay, so there is a maximal matching from A to B, right? So so all all elements of A has a pair in B. Now you can do the same thing on B. There is not, you can repeat the same thing that we did for subsets in S for subsets in B, for subsets of A for subsets of B, right? In the whole thing that we did previously, you can just replace A by B, right? Like this thing that the proof that we did earlier, for instance. Like if you pick a subset of a subset S prime of B, oh so now I understand your question. You're saying why we why this would be an why should have this, right? Is that the question? Hello?
Ma'am, actually, as of I know, there is a matching which saturates A. That means that matching should contain all the elements of A.
Yeah,
But you are
so the
saying the
matching
size of A.
contains, yeah, so the matching contains all the elements of A, right? So there is a matching, say which contains all the elements of A.
But
Okay,
it said that size of A, right?
so yeah, so if there is a matching which contains all elements of A, what is the size of A? It must be less than 2n by 2, because right, because what does it mean that there is a matching? It means the like we have a set of edges E such that one of its end is in A, another of its end is in B. Say we have a set of, say, E prime, E is the regular edge, and A occurs exactly once. In E prime. That is, and so does B, right? B occurs exactly once in E prime, right? So there is, if you have A and B, there is exactly one edge going from A and connecting B. B has no other vertices in A connected to it in the matching set, not in the edge set, right? Are you clear? Is that understood? Say if we have sets, say AK, then we have distinct vertices in B such that there is an edge between AI and BI. So corresponding to each AI, we have a BI. So we can say that the cardinality of A is less than or equal to the cardinality of B. If there is a matching there is a matching of A in B, then obviously by Hall's theorem, you have n of A less than equals the cardinality of A. And where does n of A reside? It resides in B, right? Right?
Yes, ma'am.
So this holds, right? So as we have this, what does that give? What does that give you?
Both are equal.
So we have this then. So we get the cardinality of A less than equals n. Similarly, as we have done before, we can show that the cardinality of B is dominated by the cardinality of A. And from there, we get that the cardinality of B is less than equal to the cardinality of A, right? This we get from Hall's theorem, that we have shown that this condition holds. Like in the previous what we have done before, how we have, the way we have shown that the conditions of Hall's theorem holds, we can do the same thing using we can do the same thing by replacing A with B, right? So we have the cardinality of B dominated by the cardinality of A. Again, this. So from here we get that the cardinality of A and B are the same. Is that clear?
Ma'am, why this long method is needed?
Why?
Can we do in this way? if we take cardinality of A equal to K.
Hmm.
Hello?
Yeah, I'm listening.
Hello? If
Yeah,
cardinality of A equal to K, then cardinality of B will be 2n minus K, right?
cardinality of B will be?
2n minus K, because
Yeah,
so if we count the edges in G, that is AB, right? Bipartite of AB.
yeah.
We can count it from in perspective of A, or we can count it in perspective of B, right?
Yeah.
So if we do it in perspective of A, then it will be 10K total number of edges.
Yeah.
In G.
Yeah.
Right?
Yeah.
If we take in perspective of B, it will be 10 into 2n minus K.
Yeah.
So these both are equal because the number of edges will be same, right?
Yeah. So that the number of ages are the same.
Then it will
That's what.
be K equal to 2n minus K. That is 2K equal to 2n. That is K equal to n. So
Yeah.
if cardinality of A equal to n, then cardinality of B also will be n. Right?
I 2K equal. What do you say?
The number of edges, if we take cardinality of A equal to K,
Yeah.
the number of edges in G will
Yeah.
be
Yeah. Yeah.
10 into K, right?
Yeah. Yeah.
Then the cardinality of B will be 2n minus K because the total number of
Yeah. 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 Yeah.
uh,
Yeah. It's
then
fine.
it will be
You
the
can
number of
do.
edges will be 10 into 2n minus K. Since
Yeah.
this number of edges are equal, therefore these two must be equal.
Yeah. Yeah. So basically, you can't just say it from the number of you can't just say it from the number of ages like yeah. So basically, yeah, that is fine. Yeah. So it is fine. What you said. So so now that you've shown that the cardinalities of these two are the same, so since we have a matching that covers all of A, it must be a perfect matching. Okay. So is that fine? Hello.
Yes, ma'am, I understood.
Okay. So we'll end here today. And
Yes, ma'am. Ma'am, if possible, can you share the answers? Answers means we can check the first, second, third, fourth also, those things also.
okay. We'll what you're saying you wanted the checked scripts, you wanted the marks.
No. Answers, not check strips.
Oh, you want me to like write down the answers and send it to you?
If it is there, if it is not there, no need. But if it is there, because just we want to check.
Oh, it's not there, but
So
like if you want we can do that.
it will be difficult for you, right? Means to write and all.
Yeah, so like if there's a confusion, like we're at ACMU, you can just drop by sometimes.
Okay, ma'am. Which one, ma'am?
Sixth floor, uh
Dean's office building.
no, the other dinosaur building, the PGDBA building.
Okay, that okay. Machine learning unit will be there.
Machine
Machine
learning
intelligence.
unit building.
Fourth floor, machine intelligence unit. Okay, okay, ma'am.
Yeah. So we are at sixth floor. You can come by in time.
Your name is, ma'am, Sutanoya,
Yeah.
right?
Yeah.
Thank you, ma'am.
Okay. So we'll end here. We'll see you in the next class.
Thank you, ma'am.